Okay, so now it is the time to start. Thank you very much for coming to this new session of the European Non-Associative Algebra Seminar. And for me, it's a great pleasure to introduce to you Marco Trombetti from the Università degli Studi di Napoli Federico II. He's a he's a very active researcher in algebra, mainly in group theory, but very recently he has made some nice contributions to the scope of skew left braces. And well, he has probably he has more than 80 publications, although he's very young. And well, he will speak about the title of his talk is on cardinalities whose arithmetical properties determine the structure of solutions of the Yang Baxter equation. Whenever you want, Marco.
Thank you, Ramon. Thank you for the nice introduction. Also, let me thank Ivan for the invitation to speak to you. And thank you, everybody, for being here, following me. I know it's, quite hot, so I can understand. It's difficult to listen to a talk in these conditions. But anyway. Okay, so I'm going to talk about cardinality with arithmetical property determine the structure of a solution of the Yang Baxter equation. It's a very long title and is based on a joint work with Maria Ferrara and Cindy Tsang. This paper is still on the archive, but we hope it will be soon appear somewhere. And so first, let's start. I will give for granted that, basic things about the Yang Baxter equation and the skew braces are known by now, because I think it's already time to assume that the basics should be known, but still I will give you some hints about this, just to fix notation. So what is a solution, or for better say, a non-degenerate set-theoretic solution of the Yang Baxter equation? For me, this is a pair made by two objects. We have a set X and we have a function R. And the function R is a function that goes from x times x to x times x, and the components are written like this. And R should be bijective. This is just the content of solution of Yang Baxter equation. And this thing should hold. I will not give details, but R1, 2 means that this is an equation made on x times x times x, so x to the third, on the Cartesian power x to the third. And it should be pretty self-explanatory. And the components here, these maps here are bijectives. Some notation that we also would need. Well, a set-theoretic solution, I will just say solution without non-degenerate and set-theoretic. So I will just speak about solutions right now. And I will say that the solution is involutive if the map R times R is equal to the density. If this condition holds. And I will say that the solution is the flip if it flips the coordinates. And this is a very trivial kind of solution. You can always find in every set, if you impose this condition, then you get a solution for the Yang Baxter equation. So far, so good. So one of the biggest problems in the theory of Yang Baxter equation, which comes from the world of mathematical physics. I'm not really interested in mathematical physics, but you will see, and you will probably know why this is something that also interests algebraists. Well, one of the biggest problems, as I was saying, is to classify many relevant classes of solutions of the Yang Baxter equations. But there is one problem, one little problem. The problem is that up to isomorphisms, what you get, for example, this number of involutive solution of cardinality 9, which is, still not very nice. Or maybe you get this other number, 4 million something, almost 5 million something solution, involutive solution of cardinality 10. This is something still not nice. And you get, if you want to also consider the non-involutive ones, you get 400 million solutions of cardinality 8. So it's clear that this problem is not attackable by Tsang. I mean, you should find some path that will simplify, that will scale the problem. Okay, and one thing that has been found, uh, you probably know Beramp, Leandro Vendramin, and Guarnieri, and many others, is that you can scale the problem by considering an algebraic structure which is name goes under the name of skew brace. So what is a skew brace? A skew brace is essentially a set with two group structures linked by a skew distributivity property, which is, this is actually the definition of a left skew brace. There is also a right skew brace if you require that the distributivity relation is on the right instead on the left. But I prefer to speak about left skew brace. For example, I think Ramp and also Andrea Caranti, they like more the right skew braces, but just this is me. And just to fix some notation, okay, here you get the plus, but you should know that the plus is not a billion necessary. If this thing is a billion, then you just speak of a brace instead of a skew brace. But anyway. Some other notation is that if you get a skew brace, then this map here, this function here, is actually an automorphism of the additive group. And you also get that the map assigning to every element of B, the previous map I was telling you, lambda subscript A, this is also a homomorphism. Not in general an automorphism, but just a homomorphism. And you can consider also, as usual, as in radical ring, and for example, radical ring are a very basic example of skew braces. There is a third operation, which is the star product. It's called the star product. And this star operation measures in some ways the difference between the plus and the circle. So, I mean, you can read it directly from the definition that it says how, in some sense, if there are many non-zero stars, the skew brace is very non-trivial, where trivial means that the operation plus and circle coincides. Okay. And well, some other definition that we will need in our discussion is that B is two-sided if also the right skew distributivity holds. So not only the left, but also the right. And those are very nice, actually. Two-sided cases, those are very, very, very nice objects because you can do a lot of things. The skew brace is called bi-skew brace. If you swap circle and plus, you still get the skew brace. So a bi-skew brace means just that you can swap plus and circle and you get another skew brace. Not necessarily the same, they can, but it's still a skew brace. I mean, it still satisfies the left skew distributivity. And actually, in this respect, I think we have noticed here in this paper with Andrea Caranti, Ilaria del Corso, Maria Ferrara, Massimiliano Di Matteo, we noticed that being bi-skew brace means that these maps here, the lambda automorphism of the additive groups, they need to be skew brace automorphisms. So being bi-skew brace is equivalent to requiring that lambdas here are skew brace isomorphisms and not just automorphism of the additive structure. And also another notion that we need is the notion of lambda homomorphic, where lambda homomorphic means that this function in number 2 is not only a homomorphism of the multiplicative group in the automorphism group of the additive, but is also an automorphism of an homomorphism of the additive group of B to the automorphism group of the additive group of B. And maybe there is something more. Yes. Well, this is something also which is very common. So if I say that the skew brace is of X type, where X is a property, for example, abelianity, it just means that the additive group has that property. So if I speak of a skew brace of abelian type, I'm just saying that the additive group is a abelian type, is a abelian. So a brace in the ramp terminology is just a skew brace of abelian type. Okay, so far so good. And now why skew braces? What is the relation between skew braces and a solution to the Yang Baxter equation? Well, I will not get into the details, but you just need to understand that solutions give skew braces, and that a skew brace is the underlying set of a solution. So you can just guess from the way I wrote these things that the correspondence is not bijective here. But still, there is a relation. If you get a solution and you take the skew brace, the corresponding skew brace here, then you can control in some ways the solution by the property of the skew brace. And also here, if you have a skew brace, which is the underlying set of a solution, then you can control the solution with the property of the skew brace. So although the correspondence is not bijective, you still retain some control on the solution by looking at the skew brace. So let's see if we have scaled the problem in the right way. Well, up to isomorphisms, there are four skew braces of abelian type of cardinality 9, which abelian type correspond to involutive solutions. So this is why I put this cardinality 9 of abelian type here, because if you remember, we got that many. I will just show you. Cardinality 9, you got 300,000, involutive solutions. So it's very nice now, because you just get 4 skew braces of cardinality 9, and then you get 2 skew braces of cardinality 10. Still nice. And then you get 8 skew braces of 20 skew braces of cardinality 8, which are the also involutive and non-involutive, correspond to involutive and non-involutive solutions. Okay, here. Okay, so far so good, but maybe you got still some problem. Why? Because if you go to cardinality 24, then you get 855, which is still okay. Okay, so this is why I put it in orange, because not bad. But if you go to cardinality 32, for example, then you get a lot of them. You get really a lot of them. 1 million is excessive, in my opinion, for cardinality 22, for an object of cardinality 22. If you consider that, for example, in group theory, I come from the group theory world. So for me, cardinality 24, there are just 15 groups, and in cardinality 32, there are 51. So it's a very huge step moving from groups to skew braces, although skew braces are just made from 2 groups, apparently, and no other things. So the thing is, how can we scale again the problem? Well, let's have a look to the skew braces up to cardinality 6, 3. I have this nice diagram, and well, we can see some patterns here. For example, we can see that, for example, there are places in which you have just one skew brace. This is a logarithmic graph, so you could have some problem in reading, but still there are places, for example, 1. Of course, how many skew braces of cardinality 1 are there? Just 1. And then 2, and then 3, and then 5, 7, 11, 13. And you can notice a pattern here. You could say, well, maybe the skew braces of prime cardinality, there is just one, but not only skew braces of prime cardinality there are one, because I think I highlighted, yes, these are highlighted now. There is also 15 here, which is not a prime number, but there is just one skew brace of that cardinality. So what is the pattern here? Why in some places there are just one skew brace and in some other not? Of course, if you can describe the skew braces here, you can also describe the corresponding solution of the Yang Baxter equation. So I remember, we started from solution, we scaled to skew braces, and now we are scaling a bit down by searching some arithmetical properties on the order of skew braces that they can include they can give rise to certain classes of skew braces and so of solutions that we can really describe here. So let's think about this, and if you think a bit, it's easy to get easy, more or less easy, to get that the condition is the following one. The condition is this condition here that I put in number 2, and it says, yeah, take a natural number n, and suppose that you can write n like p1 to the alpha 1 times pt to the alpha t. So this is the prime decomposition of n. And then you get that those cube braces here are precisely identified by this condition here. So you need that all the exponents in your decomposition are 1. And you also need an additional condition, because you need that pi I does not divide, any prime in this decomposition cannot divide any other prime in the same decomposition minus 1. This is precisely what they say in this condition. For example, you see the number 15 here, and 15 is 3 times 5, and you get that 3 does not divide 5 minus 1, of course, and 5 does not divide 3 minus 1. So 15 does satisfy this thing. And what else? When you identify those properties, then you find something also really nice, because you find out that all skew braces in those particular spots, they must actually be of the same time. They must be trivial braces. I mean, they must have, well, trivial brace means that, as I told you, the operation plus and circle coincide. I just write here the same operation symbol to mean that they need to coincide. And also, I'm speaking of brace, so not only they coincide, but they must be abelian the additive group, which means essentially that this cube brace can be identified with an abelian group, actually. So now, so all those cube braces that satisfy whose order is this must be trivial cube brace, which is still nice. You can also read in the opposite direction. You could ask, what is the number n for which all cube braces of that order are trivial braces? This is another way to think about this problem. And this problem means that if you have you can also add here another condition, because you can say, let's think about in terms of solutions. You can say all skew brace solution, all solution that come from the skew brace world must be flip if and only if their cardinality, all solution of a given cardinality must be flip if and only if that cardinality satisfies this requirement here. So I mean, if you have a skew brace of a given cardinality, and you know that your cardinality satisfies this condition, you can immediately say that your solution is a flip solution, for example, which is the most basic type of solution you can think of, which is nice because it gives you an arithmetical criterion to detect these things. But this is not the end, because actually you may think, okay, but let's try to weak a bit this condition. I mean, because here we are asking that every skew brace is a trivial brace, which is quite strong requirement, no? Because you are asking that it must be trivial and of abelian type. But what happens if, for example, if we just ask that the skew brace, that all skew braces of that order are trivial, but maybe not of abelian type? Well, thing is that this is equivalent to 1. It's equivalent to asking that all skew braces are trivial and of abelian type. So you cannot really increase now. Okay, you cannot get any more orders if you just ask this. And well, trivial, of course, I mean, this is just the definition of trivial, as I told you. And what about maybe almost trivial? Because I think I didn't explain the meaning of almost trivial, but I will now do. And well, the thing is that even almost trivial is equivalent where almost trivial means that you have a skew brace which is almost trivial because you get here the two operations are one the opposite of the other, okay? Or this is the opposite in the standard terms for operations. So even if you ask that all your skew braces of that given order are almost trivial, then you get that all skew braces of that order are trivial braces. So it means that this opposite means nothing here. And also something more, I believe, because you also get that all skew braces of that order are weakly trivial, where weakly trivial means essentially that you can embed your skew brace into a direct product of something which is trivial and almost trivial. So you see where I'm going on. I'm weakening the conditions. I'm trying to find the weakest condition that will give you the strongest result. Because this is weakly trivial, of course, trivial and almost trivial implies weakly trivial. So here we get that if you ask that all skew braces of that order are weakly trivial, so a very weak condition, then you get that all skew braces of that order must be trivial and abelian. And so you get that the corresponding solutions are flips. And finally, I think there is another condition here. Yes, this is somewhat related, but it gives you one more information because it tells you that all skew braces of that order must even be one generated. Where one generated means that that there is one element of the skew brace whose only sub-skew brace containing it is the whole skew brace. So you don't also need this condition, or beside the condition one, which is a stronger condition, which says that all skew braces of that order are trivial and abelian. This also means that those must be one generator. So you get pretty much information, pretty many information on that level. One generator, okay, this definition. So on this level, on the orange level, you got many information, which is nice. But we would like also to go up to this diagram. I mean, there are many other peaks that look similar. For example, I don't know if I can see, but this is 4 and maybe 4 and 9. They look the same for me, but also 30, 34. They look very similar. So maybe one can think there is another arithmetical criterion that can allow us to take all those skew braces in the same property, maybe. And the action is actually true because we can identify precisely those I was telling you before, which is 4, 9, 25, 45, and 49. And let's think about another arithmetical criterion. At the start, you may think that maybe those those orders are just, I don't know, the power of 2 primes, because 4 is 2 times 2, 9 is 3 times t, and 25 5 times 5. But 45 is 9 times 5, right? I hope so, because I I don't remember how to do computations anymore. And so it's not just the product of 2 primes, but it should be something more. And in order to understand what's more, we should introduce some nilpotency concept for solutions and for skew braces. Let's see. So let's start. What is a permutation solution? Because, spoiler alert, but if you look at those things here, those corresponds to solutions which are multipermutation solutions, which are this multipermutation thing is a nice nilpotency concept. And it is many expect that understanding multipermutation solutions would make us understand many, really many solutions, because they computed that multipermutation solutions are not the majority, let's say, but there are pretty many solutions which are multipermutation. So if you can investigate this problem better, maybe this could serve also as a framework to specifically address the problem of saying that multi-permutation solutions are, I mean, not the majority, but a really big class of solutions. I mean, to understand how big is these solutions. So let's see what is a multi-permutation solution. Well, take a solution of the Yang Baxter equation. Of course, by solution, I mean always non-degenerate and bijective. And well, it's easy to see that this is an equivalent relation, an equivalence relations. And if you get an equivalence relation, then you will take the quotient structure. So in this case, we consider the retraction, which is actually a nice way to say the quotient structure here. And on the quotient structure, you can define you find out that the map R the induced R map overline bar R is well defined as well. And this is called the retraction solution because it obviously satisfies the Yang Baxter equation. So far, so good. And this retraction will serve those of you who knows the nilpotency concept in group theory or maybe in ring theory, they know that most of the nilpotency and solubility concepts are defined by iterating stuffs, iterating substructures or iterating quotients, for example. And in this case, we do something similar because if you want to define a multi-permutation solution, you need to recursively define the retractions. So you get, for example, we just put for definition, the zero retraction of the solution is just the solution itself. And you define the n+1 retraction by taking the retraction of the nth retraction of the solution. And at this point, you say that the solution is multi-permutation if at some point, after doing a lot of these retractions, but finitely many, you get just a solution with one element, which is one of the most basic solutions that you get. And of course, the solution with one element can only be, in some sense, the flip, but of course, there is just one element, so you are not really flipping anything here properly, but it's just the solution. Okay, so those are the multi-permutation solutions. And let's think about what do they correspond in terms of skew braces? Well, in order to understand this, let's take again a skew brace, and we need to identify some substructures as I was telling you. And in this case, we get this thing here, which is named the socle of the skew brace. The socle is not a very nice term, in my opinion, because I mean I'm come from the world of group theory, but also from ring theory. The socle for me is just the subgroup or the subring generated by all the minima substructures which are normal and so. So it's not does not have anything to do with that stuff here. I don't know why they introduced it with that name, but anyway, this is now standard term. And the socle is just the intersection of the kernel of the lambda function. Remember that lambda was a function from the multiplicative group of B into the automorphism group of the additive group of B. And we need to intersect this kernel of lambda with the additive center. So with the center of the additive group. So the socle essentially is the set of all elements that centralize additively all other elements and that also act trivially by lambda action on all other elements of B. And it turns out that this thing here, this subset here, is an ideal of the skew brace. What ideal is just, you should just think of an ideal as the analogous of the ideal in ring theory or a normal subgroup in group theory, because it's just something that allows you to take quotient, for example, and that behaves well under many respects. In fact, an ideal is a subset and an empty subset, if you want, of the subskew brace, which is a normal additive subgroup and normal multiplicative subgroup, and is also fixed by, stabilized by the lambda action of B. So this is an ideal, and it turns out that allows to take quotient on all the nice thing I told you before. And well, you get the circle, but we need to define an nilpotency concept here. So as I told you before, we need to iterate because nilpotency goes iterating. And so you need to define, well, I did not write it, but the zero circle is just the sub-skew brace or the subset, if you wish, made by the zero of the skew brace, which also coincides with the one of the skew brace, but you should probably know that. And then you define the I plus one term of the circle series, of the upper circle series, I will say, by recursion, by putting this stuff here. So you want to define this numerator, and you just say, okay, take the circle of this structure of this quotient here, and by, well, non-fact, you can write this as a sub-object of B. And so this numerator is the idea you are looking for. Well, having done so, you say that your skew brace B has finite multipermutation level if and only if it coincides with some term of the upper circle series, with some term of finite type, I will say, because for some reasons, I will not tell you the reasons, but this thing here must be a natural number. And well, you see, there are some dichotomy here. I mean, because the multi-permutation solutions are defined through descending chains, something that is restricting and goes to thing that is made by one element. And here we are going to the other part. We are starting from the zero sub-skew brace, and we are going up to the whole skew brace B. This is what we are going on. But surprisingly enough, you will see that there is this nice theorem. I think this theorem is in some paper of also of Adolfo Ramon Vincent, I think, but Ramon will confirm me that later, but I think so. And it says that these solutions, this skew brace solution, which is a solution that comes from the skew brace world, and it's a multi-permutation solution if and only if the associated skew brace is of finite multi-permutational level. So those two nilpotency concepts, one for the skew brace and the other for the solution, those are essentially equivalent. And now that I've introduced this concept, well, I can show you the condition that in the previous graph, in the previous diagram, we need. So the condition that identified those green spots in the diagram is this. So you need, again, take n to be the natural number, consider P1, alpha 1, Pt, alpha t, the prime factorization. And then you need, in order to describe those green spots in the diagram, you need that your exponent must be less than or equal to 2. And then you also need that a condition similar to the previous one. And in fact, this condition 2, of course, is implied by the previous condition I told. So not only this condition describe the green spots, but it also take account of the orange ones, which were the ones we were considering at the beginning. But anyway, it says that Pi does not divide Pj alpha j minus 1. So any prime here cannot divide the full power of any other prime minus 1 in some terms. And this condition here is equivalent, as I spoiled you some times ago, to the fact that every skew brace solutions of that given cardinality is multi-permutation. So if you take, and as usual, you can read also in the other way. So you say, okay, I have a cardinality n. What is the property of my solutions, that came from the skew brace world? Well, it turns out that if your solution satisfies this thing here, for example, it is, I think I told you it was not 15, but I don't remember, 45, something like this. I can check. Let me check. what was the number I would told you? Yeah, 45. Yeah, if your solution has 45 as order 45, then it must be multi-permutation solution. So you don't need any check. You don't need to check this condition about the attractions, which can be very difficult to check. This is not easy to check. Even if you get a solution which is order 45, well, maybe by computer is easy, but by hand it is not at all easy. So, man. So this thing you get, and of course, I know before saying you something else, let's keep talking about solutions. And when we noticed this, we said, oh, but maybe all those solutions are actually stronger because the solution there actually looked stronger than multi-permutation was because they had some more properties. They also are involutive. So if you ask that all your skew-based solutions of a given cardinality are involutive, which is not a really strict restriction actually, because you saw there are many involutive solutions, well, you also get that your skew-based solution are multi-permutation, and the converse. So there must be multi-permutation and involutive. So those of order 45 are involutive and multi-permutation, which is okay. And let's now translate this in terms of skew braces. As I told you before, if you get that your skew brace of order n are a finite multi-permutational level, this means this is equivalent, this is easy, this is obvious by the theorem I showed before that this condition 4 is equivalent to the condition 1. So all your skew braces are nilpotent in some sense of given order n, if and only if this condition on its order are satisfied. And actually we can even weak again those conditions as we did before. I mean, instead of requiring that your skew brace, that all your skew braces of a given order have finite multi-permutation level, you can maybe require that those skew braces are right nilpotent. I will not go into details of what is the meaning of right nilpotent, but it's just you can think of finite multimutational level without the nilpotency of the additive group. Let's just say this. It is not really relevant, it's not that important to give the precise definition. But you can also have something actually stronger here, because it turns out that all skew braces of order n are also annihilator nilpotent. This concept, this is one of the strongest nilpotency concepts you can get for skew brace, and it implies the finite multi-permutational level and can be defined by using another kind of ideal instead of the so-called of iterated ideals, instead of the so-called, which is the annihilator or the center of the skew brace. Here the notation is not totally standard because someone like to call annihilator nilpotent, some other center nilpotent. I like both. Annihilator is more can be understood by ring people, but central nilpotency maybe can be more understandable by group theory people. So both terms have their pros and cons. So it's okay. But you get also that they satisfy this very strong condition. And we can also think of translating skew brace solution of cardinality and is involutive in terms of skew brace, but I already told you this means just that your skew brace is of abelian type. So if all your skew braces are of abelian type, then you get that this condition satisfies and converse, and vice versa. If this condition is satisfied, your solution is involutive and multi-permutation, so your associated skew brace is of abelian type, right nilpotent, which is very strong, very strong. I mean, not trivial, but very strong still. And there is also another thing, because surprisingly enough, this is also equivalent to require that all your skew braces are two-sided. So if you ask that every skew brace of order n is two-sided, then this is the condition you're looking for. So not only of abelian type, but must be also two-sided. Notice that, for example, skew braces was multiplicative group is abelian. Those are automatically two-sided. So, for example, if you ask that all your skew braces of have a multiplicative abelian group, then you will also come out with this condition here. And this is, I don't know if it's the last. No, it's not the last, but you can replace two-sided with the bi-skew brace. So your skew brace has many properties. It's not trivial. They are not trivial because if they were trivial, they would fit in the other criterion, in the orange criterion. So those skew braces satisfy all those very strong conditions, but they're still not very trivial, which is strange for me because when you get many properties, you should say, okay, this is a very easy thing to deal with, but for skew braces, it's not. Even when you get a lot of properties, it could be hard to work by hand with the skew brace objects. And last but not least, they are lambda homomorphics. Yeah, where lambda homomorphic I introduced you before. Okay, so this is what we have characterized so far, but we were not happy. We were not happy because we wanted at least do something more. The others, as you can see, up to order 6-3, I did not check the other orders, but I mean, things start to be a little wild, little less controllable, because you may see maybe order 6, order 10, order 12. Those look similar, but there are slight possibilities for other skew braces. So I don't know. What we have done is classified, find a criterion for those numbers in red, because apparently there is something that describes all those other orders. So you see, this will be our last criterion, I mean, arithmetical criterion, but up to order 16, 63, well, it gets a lot of skew braces. It gets a lot of skew braces. So we were happy also because if you want to do more, you should devise some very not natural criterion probably, but I mean, for example, we will never expect to classify those skew braces to get in our criterion those skew braces over the 32, perhaps. But anyway, how did we do? How did we classify those orders? Well, we need to first think of a natural skew brace criterion, which is supersolvability. Well, supersolvability is something that we introduced with Adolfo, Ramon, Maria, and Vincent in this work here. And it just says that let's think about a finite skew brace, because we actually introduced the concept of supersolvability for arbitrary skew braces, but for finite skew braces, it's particularly nice because it says that you got a sequence of ideals, connect the zero subskew brace to the whole skew brace, and in which the quotients, the thing here, have prime order. So this quotient here may be 2, and the other may be 3, and the other may be 4, and so on, and so on, and so on. What is so nice about supersolvable skew brace? Well, for example, turns out that every skew brace of square free order is supersolvable, which is nice. So if you have many nice properties for your supersolvable skew brace, then you have those properties for square free order skew braces, which is nice. And if you think in this diagram here, if you just look at the red things, you will see that most of them are square free, have a square free order. But for example, I think 6-3 should be not of square free order because it's 3 times 7 times 9. So those are not only skew brace, but we thought about supersolvability because we said, oh, okay, many of them are square free. And we proved that supersolvable are square free. So we said, okay, maybe there is some connection here. Also, another thing which I think is very nice about supersolvable skew brace in the that I did not expect to hold actually, because hubris behaves not very nice, but with respect to groups, for example, is that supersoluble skew brace, finite supersoluble skew brace, have zero towers, which means essentially that you can move the prime orders of the quotients, and you can get in such a way that the ones on the left are larger than the ones on the right. So you can do this thing. So you can always do in such a way that the prime 2 appears on the top of this chain. This is just the meaning of silo towers. You can get that those thing appears here and not on the bottom, on the left. Okay, so let's go back here. And I must also tell you, oh, let's just first have another look. And this is the criterion. This is the criterion we deduced from those numbers. It's far more complicated than the other ones. And it also includes actually the other ones, because all the other two criterions imply, the other two criterions imply this criterion here. I will not read this criterion. I mean, it's technical in some sense, because in order to get this criterion satisfies, you need to find example, you need to find skew brace that goes against it, goes against the property. I mean, if you need to prove that this criterion is equivalent to all skew braces of a given order to satisfy a property, well, you need to work both directions. So you need to find examples, many examples of skew braces that do not satisfy your properties and that have that given order. And in fact, one of the way we did this in the paper is by introducing many new construction of semi-direct product of skew braces and related stuff. Anyway, I will not read this criterion, but I will just tell you that this is equivalent to requiring that every skew brace of that given order is supersolvable. And should also mention something here, because we in the paper we also have introduced the concept of supersolvable solution for a skew brace, and so you get, for example, that if this criterion is satisfied, then your solution is supersolvable. I will not give you the precise details, but you can read it in the paper, because the supersolubility for the solution is technical, so I don't want to really deal with it. I'm start to feeling it. And I think there is one open problem, which is, of course, it's very hard, because you can think, okay, we thought about nilpotency conditions, but what about solubility condition? Well, can we describe the orders such that every skew brace is soluble in some sense? There are many sense in which a skew brace can be soluble. Two are the means, which are, one is the weakest and the other is the soluble, the strongest one. But this is difficult because you need to find an example of skew braces which are not solvable if you want to do this. And so you need to find example of simple skew braces which are not very understandable right now. And I think that's all. Thank you.
Okay, thank you very much, Marco, for this nice talk. Congratulations. Are there any questions, remarks, comments?
Mm.
Mm. Maybe as I would like to make a small comment. When you presented the graph with with the numbers of skew braces
Yeah.
of the different orders, perhaps, well, you said you compare them with the number of groups of this order, but perhaps I think I would compare this with the number of groups of order the square of the number of the brace. So,
Oh yeah, of course, of course. Of course. But still, if you do even if you do with the square, is not
yeah,
enough that they will not reach the
yeah,
the number of
of course, for
squares.
yes, of course, for the 30, for the 32, we have a number of groups of order 1020 and 24. Maybe this is a mm, probably a quite high fraction
Yes,
of this, at least in the logarithmic, in the log scale.
yes, yes,
Um,
yes.
but of course, for example, for order 64, we don't know the number of groups of order of 490 and
Of course.
96. Perhaps if you consider this the semi-direct product of the multiplicative and the additive group, you you get a group of this order. Well,
Probably
with
yes.
respect to yes, with respect to the and with respect to the fact that knowing that all groups of all braces of some order are soluble, for example, you know that there are braces of prime power order that are not soluble.
Of course.
This this is an example of how hard this question is. Okay? Hmm.
Indeed, 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 indeed.
All right.
Yeah, those
And
are you get some orders in which you think that this hubris should really behave, but does not.
no, yeah, not it's difficult.
Yes, yes.
Yes, I'm completely convinced of this. Are there more questions or remarks? So let's thank again Marco for this
Thank
very
you.
nice presentation. And well, so we will meet next week on another edition of the European of this European non-associative seminar, and this weekend in the non-associative, and this Friday in the non-associative day in Madrid. Thank you very much. Bye bye. Oh, there is something on the okay.